Please welcome Olaf Hartong, defensive specialist and security researcher at Falcon Force. A veteran of blue and purple team operations, Olaf has shared his insights at different cons all over the world and built popular tools used by many. Thank you for that. Today he presents I'm in your logs now, deceiving your analysts and blinding your EDR. Olaf will show how carefully crafted event tracing for Windows events can both help defenders safely simulate attacks and, if abused, mislead analysts, trigger event capping, and even blind Microsoft Defender for Endpoint with fake devices and fabricated logs. Get ready for a mind-bending session that blurs the line between defense and deception. Please give a warm BruCON welcome to Olaf Hartong. Thank you.
Thank you. All right. Cool. Thanks, everyone, for sticking around. It's Friday afternoon. People want to go home, I guess. Happy to see you here. Also happy to be here. I still love BruCON. It's one of my favorite European conferences, at least. And maybe all the other ones. For the people that don't know me, my name is Olaf, as I was introduced. Interesting to note is I'm a detection engineer by profession. I'm one of the founders of Falcon Force, which is a company that does a lot of detection engineering, but we also do a lot of red teaming. And we try to work together, internally at least, to like use that knowledge for both sides, right? I went to art school, so I used to be a documentary photographer. I even took pictures at events like these. And at some point I fell into security, which I kind of like to do as well. Last summer I was in Slovenia and I drove through this tiny, tiny little city, but I like the sign so much, especially with this talk. I was in log. So I ran out and my kids took my picture here. Useless information, but I kind of liked it. I, of course, also like warm hugs. Thank you, Disney. So move on. Couple of things I want to talk to you about a little bit today. So I want to highlight a couple of things about event tracing for Windows. I won't do a deep dive because that's probably way longer than the hour that I have anyway. Then I'll highlight a little bit why would security tools use this or security products. Then I was kind of curious if I could spoof events. Well, of course, spoiler alert, I'm here, so I could. And then I was kind of curious about how can I abuse this, because my intention was not necessarily to abuse this thing, but to use it for my advantage as a detection engineer. I want to make sure that my detections work, so I wanted to trigger certain attacks without actually executing the malware on a system, so that I could see if my detection rule would still trigger based on the logs that were generated. That was the initial intent. But then I got sidetracked and I found all kinds of other weird shit. And I have some explanations on what you can do or cannot do about this. It's primarily a Microsoft problem. But to highlight it a little bit first, so what is event tracing for Windows? So it's primarily a telemetry mechanism in the kernel. So it's very deeply ingrained in the operating system itself that can generate and expose telemetry from the user mode, so any applications that you have, but also from kernel mode drivers. And it's interesting to note, this is from the Microsoft website, it has been designed for performance monitoring and debugging. So never security, right? That came years later. So now it's used for security, but it might not be as secure. So it's implemented deep within Windows. It has its own subkernel into the NTDLL, so basically the Windows kernel. And it has a couple of main components. So there is event providers, so these provide the telemetry. Then there's the trace sessions, which are created by a request from these consumers. So you have consumers, that is a program or event log.exe, whatever. They can request a session from certain providers, and then that gets connected. And how that looks is a little bit like this. So you have all kinds of user mode providers, which is a very, very long list. The same applies from kernel mode providers, so these are just operating system components, drivers, these kinds of things. And then in the middle is the session controller, or the ETW kernel. That takes care of all the logistics of connecting a provider to a consumer, to a trace session. And there is some security there. So how that practically works, I have a consumer, whatever it is, can be any program. I can talk to the NTOS kernel. They will defer me to the ETW kernel, where I say, hey, I want to start a trace. I want to get data. So what happens then is basically the ETW kernel can set up a couple of different types of sessions. So you have an autologger session, which is started at boot, which is out of scope for now. We're primarily interested in the real-time session, right? So that's a session that is, as it says, real-time. It will still create a file on disk as a temporary buffer, but it's different than the file logging session because you can only talk to the file that is created and you can't consume like in real time. So from an EDR perspective, that's kind of useless. There are also private sessions, which are trace logger sessions or trace logging sessions. And these are primarily built for internal app monitoring. So even EDRs use these. And up until yesterday, Defender for Endpoint also had it publicly accessible. So you could actually tap into that private session, fiddle with that, and also consume the information that would be sent to the cloud. So before it was sent. But they sadly fixed that too, or actually good, right? That's a good thing. But my demo failed due to that, so that was sad. And if you create a session, and particularly if you create a real-time session that kind of looks like this in a logical flow, technically it works a bit different. But every session also gets a buffer pool assigned. And why that's important, I'll get back to that later, but just keep in mind that buffers are a thing here. And of course, I'm not the first one to play with ETW, right? There's a lot of ETW attacks from an offensive perspective, but they always go after the consuming part of the generation. So you can patch the kernel in memory and block some of those write functions, which is very common in MZ bypass attacks. You can tamper with these files on disk. You can block specific events by hooking functions in the applications that you want to protect from being logged from. Or you can disable trace sessions. And particularly the last one needs kernel level access, right? You need to have local admin privileges, load a vulnerable driver, and all that kind of stuff. And that basically applies for all of these attacks. You need quite high privileges in general to do this, which was something I didn't want to do. I want to do everything unelevated from user mode, because that's the most likely to be abused if you're a phisher or some attacker, right? So on initial access, I already want to be invisible. So why do they use this in the first place? As if it's already, there's quite some attack surface with it, right? So I think one of the reasons is stability. So since ETW is a separate process within the kernel, you can't execute code through it. You don't need to inject into anything. So yeah, that's also a stability factor, right? We've seen what could happen if you make a mistake in the kernel as an EDR, and you can take down a lot of things. So that's one of the reasons why you might not want to use kernel for everything, because people can make mistakes. Another really good thing is performance. So these trace sessions are extremely performant. They're in a very low end of the kernel. They have their own buffered memory. So it's quite efficient to actually get that telemetry from there. And another cool side aspect of it is ETW traces. You can really specify, I only want to need these event IDs with these specific processes or whatever you're interested in. Whereas with kernel callbacks, you just can enable it or not, right? You get everything or nothing. So that's a big difference. There's also a reliability factor, which might bite it in the butt later on. But kernel callbacks are just streamed. They're just instantly streamed. There's no buffering around it. And ETW sessions, as I mentioned earlier, they get a buffer pool assigned. So if your machine is busy doing something, then at least the event at some point will arrive. Then another big benefit for the vendors is there's dynamic control, right? So it's just enabling another ETW provider in your configuration. You don't need to make any code changes. You don't need to push new software. You just need to update the config, and you get more telemetry or less, for that matter. So it's way more flexible for them. And the big other one, of course, is the coverage breadth. So if you look at what kernel callbacks can give you, it's only a subset. It's like 12 different things or something, whereas there's an ETW provider for everything. So there's way more telemetry to be gathered. And it's also less intrusive, right? You just talk to the kernel and say, like, hey, I want information from this. You don't need to hook functions or inject into processes or these kinds of things. You still need to do that, but you don't need to do that as abundantly. So there's a big benefit. So there's a lot of examples about Microsoft Defender for Endpoint in this talk. Microsoft explicitly told me to tell that it's not a Microsoft problem. That is actually true. That's not the reason why I want to say this, but think along that like every EDR that has a cloud-based component will be applicable for all of the information I'm talking about, plus any EDR in general for the ETW provider stuff. So this is more, you don't need to read this, but on the left side you see the kernel callbacks that Defender for Endpoint is relying on. And the big block here is all the ETW providers they are listening to, using information from, and that kind of stuff. So it's more to highlight where most of the information comes from. So why it's important. And this is also, like CrowdStrike does the same. Any EDR uses a lot of ETW. It's just a very valuable resource for them. And they still do function hooking and these kinds of things. So what that config in a very nutshell-y thing looks like. So this is a very small component out of the Defender for Endpoint configuration. And at the top you can see like a GUID, a name, and a keyword mask of the, in this case, LDAP client ETW provider. So that's the provider that gives you every LDAP query that you do on your domain. It will log the telemetry from that and will send it out to Microsoft Cloud to be analyzed. And there's a couple of other things that are highlighted here. So you can also see that there's a capping on this. And this is what every cloud EDR does, right? You can't do like full telemetry streaming because A, that's very performance intensive, right? It hogs your bandwidth. Here we're quite lucky in most cases, not with Nestori's talk, but in most cases the bandwidth is fine in Europe, right? But this also needs to work in like low bandwidth environments, so you can't just flood every pipeline, and especially if you have like thousands of computers, at some point your bandwidth is full. But of course there's also a cost component, because all that data goes to Microsoft, they need to store it, they need to process it, and they don't charge you for that. You have like fixed fees, so they also want to make money, and a lot of it. So they also need to have like a cost balance ratio. But what you see here is that there's like a maximum of 1,000 LDAP events that is being logged from a single machine. And then there is another one where it says local capping with a number of 1 and expiration period of 24 hours. And they call it the LDAP first scene. So that's basically what they're doing, is they're only logging unique LDAP queries from a unique process, and then only 1 a day. So if you do 2 queries from the same process that are the same, you only see it once. And you can make arguments that that's very annoying. It is. If you're doing detection engineering, it's super annoying, because usually you're trying an attack several times, and then you try to correlate it, and you only see it once, and you're like, what the F, where's the data? This is where you don't have the data. You could argue that you only need to see it once to be bad to actually do something about it. That's probably also what Microsoft would say. Maybe true, but it's not ideal. But be aware of this. And this is applicable to almost any EDR that goes to the cloud. So all these things made me wonder, so look, what would happen if I can actually write my own events? So can I play with this? And then, as I mentioned in the intro, the primary thing for me was to have a way of triggering certain behavior without actually executing the behavior. Because for the EDR, it doesn't really matter if I execute something malicious or pretend, or just make the system believe that I actually did the thing. But of course, I can also use it offensively for creating all kinds of distractions, spoofing events, or maybe even go further and blind an EDR if I exceed that threshold. That was the hypothesis. You can probably do even more, but we'll get into that later. So a little bit on how that works. So ETW providers they have a globally unique ID, which you need to register, and any process in general on a system can do that for a user mode provider, even if it's already there. So that's by design. It's just a way of how it works. And each registration is process specific, and you get a unique handle for your process to that specific provider. And if you call that event register function and it already exists, you just get a handle to the existing one. So that's basically the process behind it. There's roughly 3 different ways of providers. There are MOF-based providers, which are more from the WMI time, so they're not really used anymore. The most predominant ones are the manifest-based providers. So they were introduced in Windows Vista, which wasn't a great OS, but at least this thing was good. The only bad thing about it, I guess, is they're XML-based. I'm not a real lover of XML. Probably people that are here do like it, so don't be offended. And anyway, but all these manifests are stored in the System32 folder, so you can even go through them, analyze them, and have a look. The other one are trace logging providers, and these are primarily, as I mentioned earlier, built for in-app analysis. So you don't need a manifest because you built the program, so you can just analyze the telemetry that you're generating for yourself. So that's primarily where they are used or intended to be used. So you can forget about it for the rest of the talk. And these manifests look a little bit like this, so they have a similar structure with a name, a GUID, and some other stuff in it. Then there are the event elements, so they describe all the event IDs that you can generate. And then they all have a template assigned to it. So you can have multiple event IDs that have the same structure. That's basically what that means. And one of those templates looks like this. So this is the same one for that LDAP event, right? So you can see the scope, the search filter, the distinguished name, all these kinds of things. This basically builds that template for that manifest. And that's also where the ETW kernel will check against that manifest if you send it an event. So this was probably the most work, is to reverse engineering all these kinds of things and sending the telemetry in the right way, so for the kernel to accept my not so real telemetry. So if you're more interested in finding out a lot of stuff about that, probably my favorite is ETW Explorer by Pavel. But there's a couple of other ones that are also quite useful to play with. This is the most visual one. My biggest beef with this one is that you can't select a lot of the text and copy-paste it, so you have to still type it over. But apart from that, it's amazing. So how that looks visually is, I'm using the TCP one as an example that already exists. It's connected to a real-time session, which most likely is some event log. And my process at the top calls the event register function, and I say, hey, I want to register this TCP one. And the ETW kernel knows that, so like, hey, it exists already. That's that one. Here's a handle to it, and good luck, have fun with it. So now I can write events to that same provider, and they will end up in that same real-time session that already exists. There has to be a session existing for it to be logged, right? That's sort of the premise of it, which kind of makes sense, I guess. So that's also where I can now start injecting events. So I can emit events to an existing provider from a different process, and nobody's the wiser, basically. It will just arrive, it looks the same if I did my homework correctly, and it looks like, hey, these events are actually emitted from the TCP provider, which in most cases is some operating system component. And in general, I think I haven't seen anything where you can actually see, from the ETW perspective, there's no mechanism to track which process actually emitted that event. You can see which process did that behavior, but that doesn't necessarily have to be the same process that emitted it. So you can actually spoof certain information. The only thing you sadly can't do is spoof that PID. So the PID that you see within an event is the actual PID of the process that sent that event. And that was kind of a shame, because one of the things I tried is to make MSSense think that MSSense did bad things and kill itself. But that didn't work. That's kind of handled by the kernel, so it will just override it, basically. So that was from a user mode perspective. From a kernel perspective, you can do the exact same thing. So I can register this security event log provider and start emitting stuff, but then I need a kernel driver, right? So the barrier to entry is a little bit higher, plus you need local admin permissions, and you need a signed driver to do this, so, but you can. I didn't try it, but I've seen people later, after I published this talk, that they actually showed that was possible. So if you want to do that, have fun with that as well. So there is some security on it, fortunately. Not much, but at least there's something. So every provider can register a SDDL in the registry. And basically there it can say what you can and cannot do with that provider. And there's even a fallback mechanism in there. So if you don't specify any security reasons for your provider, there is a default that it will fall to with some permissions that it will then inherit. So if you don't specify anything on your, whatever your provider is, if you want to create a custom one, it will inherit the default. And basically what happens in a high-level perspective, if I do a start trace as a consumer, the ETW kernel will have a check in the registry for that GUID to see, hey, is there a list or an access list defined for it? If not, or if you're allowed, then it will create the logger session for you. Otherwise, it will tell you to bugger off, basically. And there's a subset of things that you can set on it. So this is basically the whole list, and you can set that to a user or a group. So it's relatively flexible, but it's also limited in a way because it's primarily built for the consumer part of it. So if I want to register a provider, as I was showing earlier, that doesn't apply to this access list. And I'll get to that in a second. You don't need to look at this long. It's quite strict. So basically what this whole list means for the default is you need local admin privileges to actually start trace sessions for 99.9% of all the providers. There's a couple of exemptions. So one of them is the performance log users group, which is also, if you install Visual Studio, you will be automatically added to that with your account, even if you're not a local admin. So then you get all that permission. So you can basically do everything, which kind of makes sense because you're a developer. You need to have all these permissions to do something with it. But there might be ways to abuse that as well, because ETW is extremely useful if you want to do credential dumping, all these kinds of things as well. Don't cover it in this talk, but it's a fun exercise to play with. There's no real easy way to evaluate it, or at least I didn't find it, so I created a very simple tool to basically give it the name of a provider or the GUID, where you can dump the SDDL and make it human readable, right? Because I can't read SDDLs. There are people that can, which is impressive. But this is basically what, for instance, the anti-malware service provider has. And this is one of the exceptions where there's an allow to everyone, which is almost never the case. Usually you're not allowed to read these kind of sessions as a normal user because there might be sensitive information in there, so it's protected. The reason why this is in there, according to Microsoft, is primarily so that you can do user mode debugging or troubleshooting. So if you have issues with your EDR, they give you this MDE client analyzer toolkit that, as one of its treats, also start a trace log on this provider. What's in this provider is actually funny, and I have some slides on that later. Usually it's everyone can only register GUIDs, but you can't do anything with these GUIDs. So that's the more likely case. From a provider perspective, that kind of looks like this. So if I want to register a provider, there is some security, but not often. I tell it to the kernel, it's like, hey, I want to register this TCP provider. It will check in the kernel source code, and it will go to a get disallow list function, and it will look into a special list that it has loaded for certain providers where you can actually block access. And I learned this the hard way after I reported all this stuff to Microsoft, that I started patching things, because this is not documented. All these sub-functions were not documented, so I had to really take apart the anti-DLL for that. And then if you are not on the disallow list, then you will get a handle and you can still emit to that provider. So that's a lot of the theory. Now I started playing. So I wrote a small POC in Go. And Go is because that's the only programming language I can work with. I'm not a really good programmer, and I like Go, so that's why I used it. There's probably easier ways. If you can do C, there's actually libraries for this. So I built it. I tried it with a couple of open source packages, and all these packages, as you can see, are primarily built for consuming events. So that was sort of a limitation. So I wrote a POC, and it looked like it worked. So on the right, you can see a local trace of what I did. So I was happy. It's like, hey, cool. But I was looking at the Defender portal and I never got logs. I waited for quite a long time because it can be buffered and can be slow. But after 20 minutes, I still didn't have any data. Sorry, so I gave up. So I started looking at what I emitted and what was actually received. And then I learned that some of the headers that were set automatically by these open source packages weren't necessarily what the kernel expected. So the kernel accepted it, but NDE was smart enough not to actually do something with it. So I had to write my own implementation. Plus, there was an issue where, as a non-developer, I didn't know that almost everything in Windows is emitted as little endian. And I was emitting normal with big endian, so it was like reversed. So a lot of the stuff was not readable for the EDR to actually do something with it. So basically, I wrote everything back to syscalls, where I used the normal native Windows APIs to actually do something with it. So I did a new fake LDAP search. It still worked locally, and then after a couple of minutes, it also arrived in the cloud. So you can just search for it and it arrives, right? So the whole chain now believes this to be a real event, which was kind of cool, so I was very happy. So then I thought, okay, now it works. Now I also want to see if I can abuse it. So I went back to that capping config, where we can see that there's a local cap of each process with each search filter and a distinguished name. If that set is still the same, then you only get one per 24 hours. So I wanted to validate that, so I first created my Bamboozle EDR process, then I renamed it to canary.exe. I ran both of them with the same search query and everything, and they both arrived. So that proves the uniqueness that the capping is limited to one. I could have done it several times, so you have to believe me here that I actually did, and you only would get one event. But as soon as you rename the process, you get a secondary one. So then I played a little bit longer, and I just put some random garbled data in there that didn't really have any real meaning, and that would also arrive. So then I could actually try to fuzz it. So then I looked at, so hey, that global cap of 1,000 is also interesting. Well, what would happen if I exceed that? So of course I took the lead number and emitted that. And after a while, I saw that there were only 1,000 of them actually arriving in the cloud. So the other 337 events never made it, which is kind of useful if you want to do any other fun stuff. So I really wanted to make sure. So I created another process, the real canary, and I sent it with on the same machine. I let it generate whatever, some other data to make sure that also the search filter and all these things are different. I emitted that, and it really didn't arrive, right? So the canary is still alive, it didn't die, it wasn't killed by the EDR. So that also proved my theory that I can exceed those limits and I can actually be kind of blind, which is something that you can do. The only limitation is this is per event type, right? So I now did it for LDAP, I also have to do it for all the other ones. So in a real attack, I can do that basically if I phish somebody, I first run this, then I start running my attack, and there wouldn't be any telemetry from the ETW perspective. There will be still some telemetry from the kernel callback information, but that's only limited to process creation and some other stuff. So no telemetry, no detection. So no telemetry also means no detection for the EDR component, because they actually rely on that same telemetry stream. There's no alternative data stream for them or anything like it. If you block it from a logging perspective, it's actually also blocked for the EDR that runs in the cloud. Any local stuff for the AV is a different story, right? This is purely on the telemetry part that is used by the EDR. And of course, you can also do this from above. So I can't write C, as I mentioned, so here's where an LLM was actually useful. I gave him my Go code. It's like, hey, now this is what a BOF template looks like. Do your thing. And it actually did it from the first hit. And of course, don't use this in a production environment, but it works in my lab. Look at the code if you want and improve it, let me know. But you can do the same thing. So you can actually get your implant running, do this stuff, then after that you run SharpHound or whatever tool you like that does LDAP queries, and it won't show up anymore. That's kind of fun. So other things that you can do with this, and that depends a little bit on how the conditional access policies are set in a customer environment. So one of the things they sometimes do is not allow access if your user has high or medium risk assigned to it, right? They block access to that environment, which is actually kind of a smart thing to do. And in some cases also based on Intune data, you can look at is your device is compliant. So if your device has a high or a medium severity alert on it, you're not compliant anymore, you're not allowed on the network. That's a choice you can make. The last one, maybe you don't want to do it, but for users it's quite common. But that also means that I can maybe influence that. So later I started looking at the anti-malware service, where there's also a cap of 1,000. And I started emitting, again, 1,300 fake AV events, fake malware detections. So I have a whole bunch of malware that it didn't really happen. And again, only 1,000 are logged. So if you know you have an implant that might be detected but not killed by AV, and you want to run it for whatever reason because you're too lazy to do an AV bypass, this is a thing you could do. Of course, this will be noticed, right? If you have 1,000 malware samples detonating on a client's machine, most SOCs will notice, I hope. So that's a thing. Another thing, I can also be a ransomware operator now. If you want to disrupt an organization's capacity to respond to incidents, you shouldn't do this, but you could, is inject fake ransomware detections. And the fun bit there is for a long time, that would also generate a shit ton of alerts. And they say ransomware with a big red box. So again, a SOC person will definitely notice and maybe start panicking. So again, don't do this really, because you might make people actually traumatized. But you can. And the same you can do for other AV detections and interventions. You can even tell it to believe that I really enabled real-time protection, even though it just did. So it can also, and it will be logged. It will be visible in the portal, right? So you can disable real-time protection, tell it that you actually re-enabled it, but don't do it. Do your thing, and then actually enable it, and nobody will be the wiser. So those kind of things were kind of tricky, so I felt I should write a letter. So I wrote to MSRC, and I did that somewhere in January this year. I had a very lengthy report about all the 100 providers that I was able to abuse, including a POC tool that covered only this anti-malware bit. And the reason why I highlight it will be clear in a bit. So actually quite quickly, they responded to me. It's like, thank you, you're valuable as a researcher, but we don't really care about this, and we're not going to do anything about it because it's not really raising the bar for immediate servicing. Very, very common email that probably some of you also got for certain research, and that's usually the one that I get. It's not very motivating, but case closed, right? Or not. So at some point, I was building the deck, and I wanted to record some demos because it looks cool in a demo instead of screenshots. So I was doing the same thing. I was a ransomware guy again. And then I was actually looking at the logs. Okay, great, they arrived. Now I wanted to make a screenshot of the alerts, and it stayed empty. So I was like, huh? That's strange. So at some point, somebody at the Defender team also read my report, and they were like, yeah, that's not cool. So they blocked basically that generation from happening. I don't know how they do it, because the telemetry still arrived, right? So the engine should think this is bad. Maybe I'm suspecting they wrote a signature for the stuff that I generated, because it's quite repetitive, right? The same file name, same log directory. But I couldn't really validate that. So I was kind of happy. It's like, hey, they fixed it, cool. But then I started testing other stuff. So I went back to my favorite LDAP injection and started running fake Sharphound, fake AD Explorer, fake Certify, all these kinds of tools. And they still generated alerts. Okay, so they didn't really fix it. And this is still possible today, by the way. So you can still play with this, which can be useful for validation, for trolling your blue team, whatever. But what they also did is they wrote a AV signature for my POC tool. And that was kind of funny. And it also was a nice challenge because 10 minutes later, I think I fixed it by obfuscating all the strings in my binary and XOR it with lead, and then it worked. So I had to bypass an AV detection for my validation tool, which is kind of silly. And at some point, they were chasing me because they knew I was about to deliver this speech at Black Hat, and they were really eager to look at my deck. I think I got 12 emails from them, and I kept postponing it because I'm a kind of last-minute guy. It's like, yeah, I didn't really start my deck yet, but once it's done, you'll get it. So I think I sent them an email end of June, which for me was already early. And a couple of days later, I got this text at the top. It's like, hey, yeah, we already began rolling out a fix. And coincidentally, it's expected to reach full deployment August 7th. My Black Hat talk was August 6th, so there was some weird coincidental matches of the data there. And I really had to chase them. It's like, what are you fixing? Because I saw that cloud thing. It's like, is that it, or are you doing more? And again, that took probably 10 other emails, and the person really didn't want divulge any information. It was kind of frustrating because I wanted to help them and they didn't give me any opportunity to do so. The only thing they told me at the end was sort of a begrudgingly, hey, we're hardening our Defender product because it kind of looks bad to our users. That's sort of how I interpreted it. But they didn't care about the other stuff. So I tested it the day before my talk. I tested it a couple of weeks after my talk. I even tested it a couple of days ago. So the thing I noticed is I can still inject fake or AV detections or quarantine actions or all these kinds of things. I could still write fake MZ events, but I couldn't write any fake ransomware events anymore. So they actually killed me from registering the provider, which was a good thing. I liked it, but it was exactly that little thing that I sent in my POC tool and not the hundreds of others that I also sent. So they still got 99 problems and they only fixed one. So it was like really poor way of doing it. The only cool way of doing it was that they protected it via that ETW kernel bit. So there's really no way around it, apart from maybe injecting into MSSense, but that will be noticed. So that's kind of nice. And then after I started talking to them, they also provided like, hey, we're actually only focusing on the product. The rest is up to the product teams themselves, which basically means it probably won't be fixed. Which is kind of sad. This is the official thing, but there's nothing going to change as far as I would know. And at some point, another thing that I do is I pull the configuration, I diff it on a daily basis because they make a lot of active changes. And one of the things I noticed a couple of weeks ago is that they're now also looking at dropped events and out of sequence events, capped events, and all these kinds of things. So suddenly they're interested in what they're missing. So that's actually a good thing, right? So they're actually more involved with trying to look at it. And I tested it like 2 days or 3 days ago again. And now all of a sudden I also can't inject into the real-time protection provider anymore. So they now fixed 2 or 3 of the good things. And also the trace logging provider, which I have a POC for to inject into it in my tool, but it doesn't really work because it doesn't do anything with the information from a decision-making perspective. But they still protected it. So you can't listen to the trace provider anymore, which was kind of useful because you could see all the telemetry that it would send to the cloud. So that's a shame, but still useful. And then I started thinking, it's like, hey, I saw these buffer things, how do they actually work? So as you can recall, maybe if you create a real-time session, there's a buffer pool assigned to one of those sessions. And basically how it works in a high level, you can as a consumer, tell the kernel how big that buffer pool should be. So you can have some influence over it. So you can tell it between somewhere 64K and a megabyte and the amount of buffers that it has to keep for you. And this is all non-paged pool memory, so that you can't crash anything with it. I might call it buffer overflow sometimes, but it's not a real buffer overflow because there's no impact to the system. there are some exploits in it. So if you look at what that looks like, you can use the native logman command, and then you get like an overview of like the buffer size, how much is lost, and these kinds of things. And when I saw that lost thing, I was kind of curious, because maybe I can do something with that, right? What happens if I fill the buffer? That's basically not overflowing it, where I can technically overflow it, but then there's no impact. Maybe. So how does it work? So you have a real-time session, there's a buffer pool of X amount of those little pools in there, and with a certain size, and there are some providers connecting to it. So in this case, that's my consumer, but this can also be read as your EDR.exe. At some point, there are all kinds of events coming in, right? They go into the pool, and then at some point, your EDR will collect from the pool, and they do that quite often. So you have to be quick, and then the pool is flushed. So everything is gone, and it can do the same cycle again. So what happens if the pool is full and the consumer didn't get it out yet? Then at some point, the ETW kernel will tell the providers, hey, you can't emit anymore. Not at all, right? Not only to this session, but to any session. And that's where the impact comes. So here, it will tell every provider, if you try to register it, or if you try to emit an event, it's like, I don't have memory, because this pool is full. However, my EDR is waiting for data. It's like, hey, come on, guys, I have an empty pool, I want data, but the TCP provider or any other provider will be told, bugger off. It's not possible. And this is a documented feature in the ETW kernel. That doesn't mean it's a good feature. It's actually a very poorly designed feature, but it was meant for performance, right? It was never meant for security. So that's kind of interesting. So I started figuring out, so hey, what can I do with this? So I started writing a set of functions to just blast it with events. And I created a real-time trace session just to monitor if it actually would work. And I was kind of lazy, so I didn't connect a consumer to the trace session. So I only started a trace session for a certain set of providers, in this case the LDAP one, and I started sending like a lot of information. So at the bottom here, if you can read it, you saw my trace session. And on the left, I started blasting it with like thousands of events, and you see it show up with like a lot of, like the buffer size, and on the right, you see like the lost events filling up. Again, there's no real tools for monitoring this, so I had to write my own little ETWmon tool, which only looks like this, so you can see if there are dropped events. So there's no real benefit apart from research for it. But this was kind of concerning, right? Because if I can now block the ETW log from being emitted in the first place, also the EDR doesn't get it anymore. And that's the bigger problem. So this is something where there's nothing you can do about this. This is something that Microsoft has to fix. They have to change the whole implementation of how ETW is currently implemented in the kernel. They have to either segregate these pool sizes and only tell it, hey, you can't emit here anymore, instead of just blocking it. Because one of the things I did is I created this tool, which is on GitHub, and it allows you to like emit fake events into a bunch of providers. It can allow you to hit all these capping. It can simulate some attack tools like Sharphound and these kinds of things, but it's easy to extend. And one of the other things I built in is start a trace session for all the providers that I know Defender for Endpoint relies on, and doesn't add a consumer. And then it has another feature to just flood that trace session, and it basically blocks all these providers from generating telemetry. Which is interesting, because then your EDR is mostly blind. So it only gets the kernel callback information from there. And that's, as a defender, kind of sucky. And the good thing that you can use the tool for, and that was the primary intention, so you can emulate some real attacks, right? That's kind of nice. You don't have to execute it. You can put it in a pipeline and see if it still triggers. You need to extend it with your own attacks that you care about, but I don't think it's very difficult. Another thing you can try to do is build like a detection for somebody actually flooding it, and then you don't see anything anymore. You would get like a spike of data and then nothing anymore. That would be suspicious, but also complex, because there's also machines that are active, and then I close my laptop and there's no telemetry anymore, so you will get some false positives, which is not ideal. Another thing that you can try to do is monitor, and this is probably something you would want your EDR provider to do, is monitor for like weird provider registrations, right? A process needs to register those providers to actually emit to it. And for some of those providers, it doesn't make sense. So in my case, the anti-malware one, there's no reason for any process apart from the vendor itself to emit to that provider. If somebody registered, that's weird. And with LDAP, there's also a small subset, but with like TCP connections, that can be anything, right? So it's not possible for doing it everywhere. So the biggest thing you can do is basically annoy Microsoft and chase them to fix it, because hoping is probably not doing anything. As an attacker, it might be more evident already, but you can just emit a shit ton of events, exceed the cap, and you will be invisible for 24 hours, because those caps are reset every 24 hours after the first event that you emitted. So if you blast it now, then tomorrow afternoon at whatever the time now is, then it will be reset, so you have to do it again. The other thing you can do is flood that trace session that I showed you earlier with the buffers. And that is basically blind until there's a reboot, because that will deregister that trace session that is still full. So this is more effective, but you need admin permissions for that. That's the only thing you need the admin permissions for. You can also fake events and like annoy or distract the blue team here, and then you do your thing there, keep them busy. Or you can even yeet them off the network if they have like very strict conditional access policies. So that could be fun to do. But don't do it to your customers or your colleagues. And another thing is you can also register an infinite amount of trace sessions, because the limit is 64 on a Windows machine, so any other process can't register a trace session anymore, so again, they will be blind as well. So it's very disturbing. This is not AI, actually, but this was kind of funny by a colleague. I'll quickly remove it, because otherwise you can't sleep anymore. But sort of, the bottom line is you can't really rely on your logs, right? It's, a lot of people still actually trust their logs, but it's not always actually what you can do. You can't do anything about it, but you should be mindful of it, right? Some attacker can actually fiddle with it, create blind spots, but also create fake telemetry. I can also inject a lot of other stuff that you think, hey, this is weird, and you're spending a lot of time actually looking at it. Well, I'm still doing something else in your system, so that's never good. But there's also, sort of the knowledge that even though even the experts say that ETW shouldn't be used for this, there's no other real good source for it. So there's also something we need to deal with. And again, we need to kind of try to pressure Microsoft into fixing it, because otherwise nothing will change. And even then, if we all put pressure on it, it's quite difficult. They're very reluctant to change things in the kernel for the right reasons. At the same point, they also want all these EDR vendors to remove their kernel drivers and push them out of the kernel, because that raises stability issues, as we've seen in the past. So at some point, something's got to give, right? And somebody needs to change something. So let's try to at least fix this issue, and by pressuring Microsoft. So I definitely didn't think of all of this stuff myself. There's a lot of great researchers that have a lot of knowledge about ETW in general. Probably this is the most valuable website from Jeff, who sadly doesn't live anymore, but his website still does. This is invaluable information. He has a lot of undocumented features from the kernel in there that aren't found anywhere else, to my knowledge. So during this research, I also created like a bunch of tools. They're all on my GitHub. It's all the same thing, so it's quite easy to find. And maybe for the people that came for the abstract, sorry, because I got distracted by all the buffer stuff and so on, that it didn't fit into this talk anymore. I'm working on another talk that Microsoft doesn't know about yet. Well, now they do, but that is a tool called Poltergeist, where we reverse engineered the whole onboarding workflow and had to decrypt a lot of stuff. But basically, what we can do now is onboard fake devices into a tenant, start sending information, start generating alerts, and we can even force it to think that I'm actually your machine, and then it will isolate your machine instead of my fake machine, which is kind of wild. And that doesn't require any access to a machine, right? You can just do it. I have like a whole fake C2 where I can have it in multiple tenants even. So that's kind of wild. So that's something that probably will be maybe here next year. So that's something to be aware of that comes. And with that, I'm done. So if you have any questions, I'm happy to answer them. Thank you.
You mentioned that it caps at 1,000 events. Is it always the first events that the first 1,000 events, or is there some kind of function that is smart enough to roll over and keep the last 1,000 ones in Microsoft implementation?
No, there's so maybe not everybody heard it, but so the question was, does it always cap at the first 1,000, or is it sort of a rolling window? No, it does it on the first 1,000. So it starts counting from the first, in this case, LDAP query that it saw, and then after 1,000, it will just say, hey, enough is enough. And the limits vary per provider. So in this case, I showed 1,000 twice. It can also be 20, 400, 10,000. It really depends on what it is. So network connections, for instance, is 1,000, I think. And then they introduced a aggregate feature, which has a sublimit of 4,000. So you actually have to do 5,000 events for it to create a blind spot on the network side. So the only way to know this is to actually get the config out. And if you want that, then I encourage you to look in the registry and have some fun there. It's not encrypted, but they do make an effort to make it not directly readable, but it should be easy to do.
Thanks for the inspiration.
Thank you. I later learned actually by building that poltergeist thing that there is also an unauthenticated API that you can talk to, so you can just get it from the cloud. I'm not sure if I want to release that because it helps you, if you're a blue teamer at least, but it also helps a lot of criminal actors, so they have to figure that out themselves, I guess.
Super, thanks for the very interesting talk. In the beginning you mentioned it's mainly for cloud-based EDRs, the capping.
Yeah.
But then at the end we saw the buffer overflow thing that also impacts non-cloud EDRs.
Yeah, that impacts anything that relies on ETR. Yeah, correct.
Yeah.
So only the capping, so they only sent 1,000 in the case of the example to the cloud for analysis. But anything that happens locally, that would still be a problem if you use the buffer problem, the buffer attack. That will just make it useless.
Is Sysmon, for example, using the same technologies? Or?
So Sysmon is for 90 or 80% relying on kernel callbacks. And they have a mini filter driver, which also doesn't rely on ETW. The only ETW that I am aware of that they use is, well, actually, I'm wrong. So Sysmon itself gets its telemetry from kernel callbacks, and the DNS one is ETW. But they write all that information into an ETW private logger. So if you manage to actually fiddle with that one, it's outside of this buffer pool, but you can still break that. And then it will be blind as well. But it's significantly more work. Questions from the neighbors? Everybody's up for coffee, I think. Which makes sense. Cool, okay, then I'll call it with that. Thank you for coming.